Methods of expressing solutions. The concentration of a solution is expressed as the amount of solute present in a given amount of the solvent or solution. For example, in a salt solution, concentration of solution equals amount of a salt in a given amount of the solution. If the amount of solute is small, it is called a dilute solution. If the amount of solute is more, it is called a concentrated solution. Let us discuss about solubility of a substance. Solubility of a substance can be defined as the maximum amount of the solute in grams that will dissolve in 100 grams of solvent at a given temperature. It depends upon nature of solvent. A solute may have lower solubility in a certain solvent but a higher solubility in another solvent. Iodine crystals dissolve slightly in water but dissolve very well in alcohol. We will now try to understand factors determining solubility of a solute. Solubility depends upon the nature of the solute. For example, at 20 degrees centigrade, solubility of sodium chloride is 38 grams per 100 milliliter of water. Solubility of potassium nitrate is 30 grams per 100 milliliter. Solubility of sodium bicarbonate is 9.6 grams per 100 milliliter. And solubility of copper chloride is 77 grams per 100 milliliter. This means that at 20 degrees centigrade, copper chloride has about twice the solubility of sodium chloride. Solubility also depends upon the temperature of the solution. Generally, solubility of solids in liquid solvents increases with temperature, but the solubility of gases in liquid solvents decreases with temperature. So, we mention temperature while mentioning solubility. Let us now try to understand how temperature affects the rate of dissolution. A given amount of distilled water is poured into two separate beakers labeled as A and B. Water in beaker A is heated till 70 degrees centigrade and 1 gram salt is added to each beaker. The mixtures are stirred at the same rate. We see that the solid dissolves at a faster rate when heated. Higher the rate of stirring, higher is the rate of dissolution. When particles of one salt are grinded into fine particles and the other remains as it is, we find that finer particles dissolve faster. So, we see that the rate of dissolution depends upon these factors. That is, nature of solute, temperature, rate of stirring, and size of solute particles. Finally, let us see some applications of solubility in our daily life. That is, hot water increases the rate of dissolution of certain substances present in tea leaves. Stirring of soup dissolves the salt faster, and so on. Let us now learn how to express the concentration of a solution. It is normally expressed as mass by mass percent or as volume by volume percent. Let us first learn about expressing concentration in terms of mass by mass percent. Mass by mass percent of a solution may be defined as the number of parts by mass of one component per 100 parts by mass of the solution. If A and B are the two components of a binary solution, then mass percent of A equals WA divided by WA plus WB multiplied by 100. And mass percent of B equals WB divided by WA plus WB multiplied by 100. We will now learn about expressing solutions in terms of volume by volume percent. Volume by volume percent of a solution may be defined as the number of parts by volume of one component, that is solute or solvent, per 100 parts by volume of the solution. Mathematically, it can be written as volume percent of A equals VA divided by VA plus VB multiplied by 100. And volume percent of B equals VB divided by VA plus VB multiplied by 100. The concentration of a solution can also be expressed in terms of the mass of a particular solute dissolved in a given volume of the solution. Mathematically, it can be written as mass by volume percent of solution equals mass of solute divided by volume of solution multiplied by 100. Here is an example for you to understand this concept. A solution is prepared by dissolving 5 grams of urea in 95 grams of water. What is the mass percent of urea in the solution? Now let us have a look at the solution. Mass percent equals mass of solute divided by mass of solution multiplied by 100. Solution therefore is mass of urea equals 5 grams, mass of water 95 grams, mass of solution equals 5 plus 95 equals 100 gram. Mass percent of urea equals 5 grams divided by 100 grams multiplied by 100 equals 5%. Let us now try to understand. Strength of a solution. Strength of a solution may be defined as the amount of solute in grams present in 1 liter of the solution. Mathematically, strength is equal to mass of solute in gram divided by volume of solution in liters. Let us take an example. Mass of glucose is equal to 5 grams. Volume of solution is equal to 200 milliliter. Therefore, 200 divided by 100 is equal to 0.2 liters. Then, strength of solution is equal to 5 gram divided by 0.2 liter, which is equal to 25 grams per liter. Let us now try to solve a problem. What mass of sodium hydroxide must be dissolved in 500 milliliter of solution so that the strength of the solution may be 10 grams per liter? We will now try to find out a solution. Strength of solution equals mass of solute divided by mass of solvent multiplied by 100. Here, mass of solute is equal to 4 grams. Mass of solvent is 40 grams. Solubility, that is, in a saturated solution, is equal to 4 grams divided by 40 grams multiplied by 100 grams, which amounts to 10 grams. This means that solubility is equal to 10 grams. Here is one more problem for you to solve, and I am sure you would solve it effortlessly. A. What mass of potassium chloride would be needed to form a saturated solution in 50 grams of water at 298 Kelvin, given that solubility of the salt is 46 per 100 grams at this temperature? B. What will happen if this solution is cooled? What do you have to say for this problem? A. Mass of potassium chloride in 100 grams of water in saturated solution is equal to 46 grams. Mass of potassium chloride in 50 grams of water in saturated solution equals 46 grams divided by 100 grams multiplied by 50 grams, which equals 23 grams. And solution for B is, when the solution is cooled, the solubility of salt in water will decrease. This means that upon cooling, it will start separating from the solution in crystalline form. Let us now try to solve one more problem. The teacher instructed 3 students, A, B and C respectively, to prepare a 50% mass by volume solution of sodium hydroxide. A dissolved 50 grams of sodium hydroxide in 100 milliliter of water. B dissolved 50 grams of sodium hydroxide in 100 grams of water. The student C dissolved 50 grams of sodium hydroxide in water to make 100 milliliter of solution. Which one of them has made the desired solution and why? And the solution is C has made the desired solution. Mass by volume percent is equal to mass of solute divided by volume of solute multiplied by 100, which amounts to 50 divided by 100 multiplied by 100 equal to 50%. Here is a problem with a solution in front of you. See it and understand it. Calculate the mass of potassium sulfate required to prepare its 10% solution in 100 grams of water. Let us now try to solve it. Answer: mass percent equals mass of solute divided by volume of solute plus mass of water multiplied by 100. 10 is equal to x divided by x multiplied by 100 whole multiplied by 100, or 1 equals x divided by x plus 100 whole multiplied by 10. X plus 100 equals 10 times x, or 9 times x equals 100, or x is equal to 100 divided by 9, which amounts to 9.1 grams.
Atoms. Have you ever heard about Maharishi Kannad? Maharishi Kannad was an Indian philosopher. He had said that on breaking again and again a matter, we get the smallest particle. Later on, a scientist, Antoine Laurent Lavoisier, had proposed two laws. One was the law of conservation of mass, and the other, the law of constant proportions. British chemist John Dalton had given the basic theory related to the nature of matter. He had taken the name atoms as given by the Greeks. He had proposed that atoms are the smallest particles of matter. According to Dalton's atomic theory, it was believed that all matter is composed of small particles called atoms. Atom is the smallest particle of matter. This is a postulate of Dalton's atomic theory. Let's try to understand it with the help of an example. Let's take a stone and try to break it into small pieces. Each small piece of the stone represents an atom here. According to Dalton's atomic theory, as we know, atoms can neither be created nor be destroyed. Let's see what does it mean. Let's take a look at coal. Oxygen molecules are present in our atmosphere in gaseous form. We all are aware with this thing that coal is made up of carbon atoms. When coal is heated, carbon atom present in it goes into gaseous form. These carbon atoms combine with oxygen in atmosphere to form atmospheric carbon dioxide. The postulates of this theory may be stated as follows. All matter is made of very tiny, indivisible particles. These tiny particles are known as atoms. Atoms are indivisible and indestructible. Atoms can neither be created nor destroyed in a chemical reaction. Atoms cannot be changed into atoms of other elements. All atoms of the same element are identical. Atoms of a given element are identical both in mass and properties. Different elements have different types of atoms. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. The relative number and kinds of atoms are constant in a given compound. Atoms of same elements can combine in more than one ratio to form more than one compound. Compounds are formed from atoms of the constituent elements. Atoms are the smallest unit of an element. Atom maintains chemical identity throughout all chemical and physical changes. Chemical reactions occur when atoms are rearranged. In this way, we can say that Dalton's atomic theory suggests that the atom was indivisible and unbreakable. Let's discuss postulate of Dalton's atomic theory. Atoms of the same element are alike. Let's take an example to clear this postulate. Let's have a look on charcoal and diamond here. What is present inside charcoal and diamond? Let's see. As we know that charcoal and diamond are made up of carbon atoms, is there any similarity in carbon atom present in charcoal and diamond? Carbon atoms present in charcoal and diamond are alike or not? Let's discuss it. If we see carbon atoms at micro level, we find that carbon atoms neither present in charcoal or in diamond are of the same size. It proves that atoms of the same element are always alike. The most significant concept that Dalton's atomic theory had proposed was of the atomic mass. According to Dalton's atomic theory, each element had a characteristic atomic mass. Dalton's atomic theory was based on the laws of chemical combination. His theory also gives an explanation for the law of conservation of mass. His theory also explains the law of definite proportions. His theory also proves that each element had a unique atomic mass. If we compare the masses of carbon atoms present in charcoal and diamond with the help of beam balance, we find that in both cases, carbon atoms have same atomic masses. We see that beam is balanced. If we compare the masses of carbon atoms present in charcoal and iron atoms present in an iron piece with the help of beam balance, we find both atoms have different atomic masses. In this case, we see that beam is not balanced. Discovery of subatomic particles inside the atom led to the failure of this aspect of Dalton's atomic theory. These two fundamental particles were electrons and protons in an atom. Atom is divisible. Isotopes have slightly different masses. Today we know that atoms can be destroyed with the help of nuclear reactions. We also know that there are different kinds of atoms within an element that are known as isotopes. Isotopes of an element have the same chemical properties. According to Dalton's atomic theory, as we know, atoms of different elements differ. Let's have a look on postulate. Let's compare atoms of two different matters. As we know, charcoal is made up of carbon atoms and iron piece is made up of iron atoms. If we look at carbon and iron atoms at micro level, we find that both differ in size. When scientists started exploring matter, they realized that matter can be divided into smaller and still smaller particles. They discovered that the smallest particle of an element that maintains its chemical identity through all chemical and physical changes is called an atom. Atom was derived from the Greek word atoms, meaning indivisible. Thus, it was considered to be indivisible. Let us now discuss about the nature of atom. Atoms are made up of protons, electrons, and neutrons. Protons are positively charged particles. Electrons are negatively charged particles, and neutrons are neutral. Protons and neutrons are found in the nucleus of the atoms, while the electrons are found on the shells. Matter is anything occupying space and having mass. It is the material of the universe. Atom as a whole is electrically neutral. As you see in the animation, a carbon atom is shown. In the center, you find a nucleus consisting of protons and neutrons. Surrounding it are two orbits, where we find electrons. Protons are shown in green, whereas neutrons are shown in red. The atom, on whole, is electrically neutral. Atom is the smallest particle of an element, which can take part in a chemical reaction. It retains its chemical identity throughout all chemical and physical changes. The relative sizes of some extremely small matter are as in the table. An atom is the building block of all matter, the smallest particle of an element. More than 115 types of elements are known around us. An atom can exist in ground as well as in combined state. Noble gases exist in free state. Atoms can be seen with the help of scanning tunneling microscope. Symbol of elements. A symbol is a shorthand notation used to express an element. Dalton used to represent one atom of an element. Some of the symbols used by Dalton are as shown on the screen. There was confusion regarding the names of the elements. Initially, the names of the elements were derived from the place of their origin. Some names were given to the elements on the basis of their colors. The name gold was given because it means yellow in English. Berzelius suggested that symbols of elements should be taken from one or two letters of the name of the element. International Union of Pure and Applied Chemistry (IUPAC) nomenclature is used these days, which has guidelines for naming elements and assigning symbols. The symbol of an element consists of the first letter or the first letter and any one or other letter in its name in English. The first letter must be capitalized and the second should be in lower case. Element, symbol, boron, B, aluminium, Al, and not Al. Symbols of some elements are formed from the first letter of the name and any letter appearing later in the name. Element, symbol, chlorine, Cl and not Ch, zinc, Zn and not Zi. Let us have a look at symbols of elements represented by only first letter of the English name of the element. English name of the element. Symbols. English name of the element. Symbols. Hydrogen H, oxygen O, boron B, nitrogen N, carbon C, phosphorus P, fluorine F, sulfur S. Symbols of the elements represented by the first letter and any other letter of their Latin or German names. English name of the element. Latin or German name. Symbols. Silver, argentum, Ag. Copper, cuprum, Cu. Gold, aurum, Au. Iron, ferrum, Fe. Sodium, natrium, Na. The atomic mass standard is based on an atom of the isotope of carbon-12. Standard atom of carbon, C12, can be represented as carbon-12, 6. Mass of one carbon-12 atom is equal to 12U. When this carbon is cut into 12 equal pieces, mass of one piece of C12 carbon atom is equal to 1 by 12 times mass of one carbon-12 atom. This is further equal to 1 by 12 times 12U, which is equal to 1U. This means that relative atomic mass of an atom is equal to mass of an atom divided by 1/12th mass of a carbon-12 atom. This means that an atomic mass is the average relative mass of an element's naturally occurring atoms on a scale that uses atoms of carbon-12 as reference. Let us have a look at relative atomic masses of some elements. Element, atomic mass, U. Hydrogen, 1. Carbon, 12. Oxygen, 16. Nitrogen, 14. Magnesium, 24. Sodium, 23.